Today we're going to look at lesson 4.02, Elvira's equations. Today's objective is I can construct and solve a literal equation in 2 out of 2 problems. So we haven't talked about that term yet, what a literal equation is. So let's go over that first. We're going to look at a couple of vocabulary words here. So the first one is a literal equation, which is an equation that has several variables. So you can see some examples over here on the side where we have A equals L times W. That might look like a familiar equation to you. You might notice that that is the area of a rectangle, length times width. That second equation might be less familiar. This is the ideal gas law. Once again, just several variables that represent things. And what about this third one? Do you recognize the third equation here? We've been using this one for a lot of this year. This is the exponential equation we've been using. You might also think of this as a geometric sequence equation. And just a quick note here about why we call this a literal equation is because sometimes we call variables literals. So that's another name for a variable. You can call it a literal. So this is then a literal equation because it's made up of many variables. So when we solve a literal equation, what we mean by that is we are going to solve for one particular variable. So notice we have many variables. It isn't clear which one we should always be solving for, so it'll tell us which one we need to solve for. So this one says solve for W. So this is going to be the variable we solve for. We can do our normal circle our variable, draw our line, highlight our other terms on the same side. That tells us what we need to remove, what we need to do to get W by itself. So since we're multiplying by L, to get rid of it, we're going to divide by L. Divide both sides by L. The L's will cancel, and we get A over L equals W. Notice we don't have any numbers in there. We can't simplify anything. We can't do any calculations. All we've done is just rearrange this equation. So now instead of A being by itself, W is by itself. W equals A over L. And then one other vocabulary term here, a formula is a particular type of literal equation. A formula is when we have variables that represent things you can count or measure in real life. So again, area equals length times width. You can measure the length of a rectangle, and you can measure the width of a rectangle. And then you can multiply them both together to get the area. Similarly, this one down here, distance equals rate times time. D equals R times T. A rate is something you can measure, like how fast a car is going. You can measure that. Time, you can also measure how long that car was driving. And distance is yet another thing you can measure. You can measure how far the car went in that time. So since these are things that you can measure or count in real life, this is considered a formula. Distance equals rate times time. So we're going to look at some examples of these back at the cafeteria, Elvira's cafeteria we talked about in the last lesson. And Elvira, the cafeteria manager, likes to keep track of things she can count or measure in the cafeteria, which makes it sound like formulas might come into play. And she hopes this will improve the efficiency of the cafeteria. So here's a table of things she has decided to keep track of. And we need to help Elvira fill in the units for each of these things she wants to track. So this first one, S. S is the number of students who buy lunch in the salad line. So what are the units here? What are we counting or measuring? Let's see, that first little bit of that statement might help us know. Number of students. Well, it sounds like we're counting students there. The number of students. All right, so let's look at W. W is the number of students who buy lunch in the sandwich line. So this was the salad line. W is the sandwich line. Well, once again, we are counting students. And similarly for the following one, number of students who buy lunch in the pizza line, same idea. We are counting students here. Okay, how about F? F is a different measure. It says number of food servers in the cafeteria. What are we counting or measuring here? Sounds like we are counting food servers. So now, just stopping here, think about whether it would make sense to combine these two variables when they have different units. Can we add these together and it will make sense? Students plus servers. Or when we add these two variables together, W and P, can we add students plus students and we'll get students out of that? Let's look at M. M is the number of minutes it takes to serve lunch to all the students. What are we measuring? Or what are we counting? Looks like this is a time measure, and we are measuring the number of minutes. And this is the total number of minutes to serve lunch to all the students. Okay, let's look at C. C is the number of classes in the school. Okay, well, it sounds like we're counting classes, number of classes. And this final one, price per lunch. So this one's a combination units, because you can see there's a per here. So there's going to be units and units. So first we have price. What is price measured in? In the United States, at least. What is price measured in? We buy things in dollars. Per means divide. So dollars per, and then lunch, we're just counting lunches. So dollars per lunch. This is what we might think of as an average. Remember, an average was a sum over a count. So the sum of the price of all the lunches over a count of the lunches. This is the average. This is the average price per lunch. That's what P sub L is. And one other note here about P sub L. You might have seen this notation before, or you might not have. This little L that drops below the P, that is called a subscript. We've looked at superscripts before. Superscripts look like this. X squared, this is a superscript. X squared, or maybe 3 to the x. When we have a symbol that goes up above, we call that a superscript, because super means above. This is a subscript. The L here is a subscript. Or you might see this as like X sub 2, something like that. These are both subscripts. And the important thing to know about subscripts versus superscripts are actually an operation. We said that superscripts are exponents, right? This is x squared. We do something to x here. This is 3 to the x. We multiply 3x times. This is an operation. That is not true for subscripts. Subscripts are not operations. All they are another variable. So you'll notice here, we already had a variable called p. So we couldn't very well use p again because we wouldn't know which one we were referring to. So what we do instead is we put a little L on the bottom of it to indicate it's a different variable. This is now P sub L, price per lunch. So P sub L. All that means is this is a different measure than this P up here. It's not an operation. It doesn't mean we're doing anything with L or that L is a different variable. This is all a single variable, P sub L, and we could have named it something else. We could have named it Q. We could have named it B, but we just named it P sub L. That's all it means. It's another variable. So now that we have those units filled in, Elvira creates a new variable to track a relationship that she thinks will be useful. So you can see that variable here, A equals S plus W plus P over C. And remember, these are the variables that are used here. And we want to know, what does A represent? What is this useful thing that we think Elvira wants to measure? How can we figure that out? Well, the top of this fraction, S plus W plus P, let's see what that is. Number of students who buy lunch at the salad line, plus the number of students who buy lunch in the sandwich line, plus the number of students who buy lunch in the pizza line. If we add all three of those together, first of all, what is the units? What's the units on the top of that fraction? Students plus students plus students. If we add all those students together, we'll still get a total number of students. And in fact, that's exactly what that means, right? Total number of students who eat lunch, or who buy lunch, rather. And then let's look at what's on the bottom of that fraction. C is the number of classes in the school. We measure that in classes. So this is a count of classes. So you might recognize this from what we just talked about as an average. This is a sum over a count. We summed the number of students, we added all the students together, and then we counted the number of classes. This is an average number of students who eat lunch, who buy lunch, per class. We say per class because that is what was on the bottom of our fraction. The average number of students who buy lunch per class. So you can think of walking around to the different classes and looking and saying, this class has 30 students, and on average we would expect 27 of them to buy lunch at the school. The rest of them have brought their own lunch, or maybe they can leave campus and go somewhere for lunch. So on average, we expect about 27 of the 30, maybe. That's just an example. So what are the units here now for the average number of students per class? Well, that just sort of answers it for us, doesn't it? It's students per class. That's our units. So now we want to know, how would we solve this for S? This is a literal equation. It has several variables in it. We can draw our line, circle our variable of interest. We can highlight the other terms on the same side. And now we need to undo those terms. We need to do the inverse operations to get rid of them. So what's our first step here? Remember, we need to remove the variable that's farthest away, or the term that's farthest away from our variable of interest. So we have S here. Looks like all this stuff's on the same side of the fraction. Maybe we can get rid of this C first. So we're dividing by C. The inverse operation of that is multiply by C. Multiply both sides by C. These C's will cancel. We get A times C. I just changed the order of those. A times C equals S plus W plus P. Remember, we're still getting S by itself. So what do we do now? Well, we just need to get rid of these other variables, and we're adding both of them, right? So now we can just subtract them one at a time. We'll subtract W from both sides. These W's will cancel. Now we have AC minus W equals S plus P. And our last step, we're going to subtract P from both sides. Remember, we're getting S by itself, so we need to get rid of this other one. The inverse operation is going to be subtraction. So these two P's cancel, and overall we get AC minus W minus P equals S. That's our answer. Notice once again, we didn't have any numbers we could simplify. We didn't have any calculations we could do. We just rearranged the whole literal equation so that a different variable was by itself. Before we had A by itself, now we have S by itself. So if we look at this resulting equation, S equals AC minus W minus P, that's what we solved for in the last problem. We want to look at these units and ask, does this make sense? Does this equation still make sense even though we've rearranged it all around? So let's see. Well, S was easy. We're just counting the number of students in the solid line. This is students again. AC, that's a little more complicated. A times C. Let's see if we can figure out what that means. So A is the average number of students per class who eat lunch, or that's actually buy lunch. So if we take the average number of students per class who buy lunch, and then multiply it by C, we're going to multiply it by the number of classes in the school. So multiply it by classes. The classes units will cancel, and we're just left with students. And in fact, this is going to be the total students, right? Because if we have an average per class, how many we would expect to buy lunch, and we multiply it by the number of classes, well, you can think, if we have 3 classes and we expect 27 of them to buy lunch, it would be 3 times 27 total students who buy lunch, which would be, I can't do that in my head, 3 times 27, 81 maybe? So A times C is the total students who buy lunch. Buy lunch. That's what A times C represents. This is total students. And then these ones, again, are fairly simple. We already figured out what those are. W is the number in the sandwich line, students in the sandwich line. So students in sandwich line, we'll just call that sand. And then P was the number of students in the pizza line. Students in pizza line. So let's look at this all together and see if this makes sense. The students S, students in the salad line, equals the total number of students who buy lunch minus the students in the sandwich line minus the students in the pizza line. Well, yeah, that makes sense because those are the only 3 lines, right? So if you added all of these 3 together, you'd get the total students. Or you can take the total students minus 2 of them and get the third one. So that does make sense in terms of the units and in terms of the story we're telling. All right, so here's another useful relationship that Elvira thinks of. R equals P sub L times the quantity S plus W plus P. Here are the things those variables represent. We talked a little bit about S plus W plus P, right? We just add all those students together. And P sub L is the price per lunch. So what is R going to be overall? How do we figure out what R is? What does it mean? Well, one way I like to deal with problems like this is to look at the units, see what the units represent. So we said that when we added S, W, and P all together, we got students, right? Students plus students plus students is going to be, this is our total, our total number of students who buy lunch. And then P sub L, well, that is just the price per lunch. We called that dollars per lunch. So if we multiply those together, dollars over lunches, count of lunches, and we multiply that by total number of students, well, nothing's going to cancel, unfortunately. That doesn't make a lot of sense. None of these are the same units, so nothing will cancel there. So we have to sort of think about it and introduce a ratio that relates the number of students to the number of lunches. So how many lunches do you think each student buys? Well, we're assuming that each student buys one lunch to one student, or one lunch per student. So we can say times one lunch per student, per one student. And in fact, if that's true, there's one lunch per student, then these are sort of interchangeable, right? If one lunch is the same as one student, or every student equals one lunch, then these kind of become similar units. Each student equates to one lunch. So we use this ratio, one lunch per one student. And now, watch this, lunches cancel with lunches, students cancel with students, and we're just left with dollars. Our units here are going to be dollars. And so what does R represent? What would we be measuring in dollars if we take the price per lunch, the average price, times the number of lunches? That's going to be the total dollars, or the total prices of all the lunches. So that's how we calculate all the dollars that are brought in for the lunches. All right, so now we're going to solve this equation for P of L. Similar process we did before. Draw our line, circle our variable of interest, highlight our other terms. We know we need to get rid of that S plus W plus P. Now that's a little bit complicated. What do we do with that? Well, looks like we have P of L times some big quantity of thing, right? So if we treat this entire quantity right here as just a single thing by itself, we can say, well, it's P of L times this bunch of stuff. So maybe we just divide by this bunch of stuff. S plus W plus P on the bottom of a fraction. We'll need to do that on both sides, S plus W plus P over here. But now look at this. This whole thing will cancel, and this whole thing will cancel. Well, that was actually pretty easy. This is a single step. So we have R over S plus W plus P, and that equals P sub L. So that was actually not as hard as it maybe seemed like it was going to be. All right, so once again, we're going to ask, does this expression, does this equation make sense for P sub L? What are these units? What do they mean? So we said R is the total price of all the lunches. This is the total price of all the lunches. S plus W plus P, we've looked at that several times now. S plus W plus P is going to be total number of students, right, who buy lunches. So if we take the total price, right, that's a sum. We add all the prices of the lunches together. Total number of students, we counted up all the students. This is a count. Sum over a count, that's going to be an average, right? And look at this, price per lunch. That's an average measurement. Average price per lunch. So we have the total price, the number of lunches, the total price per lunch, or the price per lunch will be P of L. That's what we're measuring. So yes, those units totally make sense. We just rearranged the equation so that one variable is isolated instead of another one. So one final quick thought from Elvira. Elvira notices that she's using S plus WP a lot, or S plus W plus P. We're using this term a whole bunch, and maybe it would make sense to turn this into a variable on its own, so we can just put that in place of this whole phrase, in place of this whole expression. So what does T represent? We've been talking about it throughout this lesson. What do you think? What does T represent? Well, we said it's students who buy in the salad line, plus the sandwich line, plus the pizza line. That sounds like it's going to be total students who buy lunch. But notice how much easier these previous things become if we just put T in place of that. Now we could write this as P sub L equals R over T, if that's the total number of students. This is a lot simpler to work with and read. The price per lunch is the same thing as the total price of all the lunches divided by the total number of students who buy lunch. The price over number of lunches. So if we introduce another variable, it can simplify our formulas. And then our last question, what is the units, or what are the units for this new variable for T? S plus W plus P is going to be in students plus students plus students is going to be students. Total number of students is students. So let's look really quickly at a couple of examples of how to solve these. We need to solve for R, so we're going to draw our line, circle our variable of interest, highlight our other terms on the same side. So we need to get rid of that T. What do we do to get rid of the T? R times T, the inverse operation will be divide by T. Divide both sides by T. These T's cancel and we get D over T equals R. This was our distance equals rate times time formula. We've rearranged it so the rate is by itself. The rate is the distance divided by the time. Notice once again we can't simplify that. We don't have any numbers we can calculate. It's just a formula in a different order. We've rearranged the variables. Let's look at one more example. Solve this one for W. L equals W plus 9. So we'll take our same line. We're solving for W, so we want to circle that variable. We'll highlight our other terms we need to get rid of, which is just a plus 9 in this case. So the inverse operation of add is going to be subtract 9 from both sides, and we get L minus 9 equals W. Notice in this case we did have a number. We can use numbers, we can bring them around, but we were not able to simplify because we don't know what's in this variable over here, L. It just becomes L minus 9. We can't simplify that at all. So we'll just skip these next problems, go straight to our objective. Today's objective was I can construct and solve a literal equation in 2 out of 2 problems.